Hello, everybody. Welcome to this day's seminar of the European Astrobiology Institute. I'm very happy to welcome Barbara Toffoli from the German Aerospace Center in Berlin, namely from the Institute for Planetary Research. Barbara did her PhD at the University of Padua in Italy, where she also did her first postdoc from 2019 to 2021, and then she went to do another postdoc at the German Aerospace Center, where she is now employed. Her talk will be about the relevance of geomorphology and structural geology in the search for habitable environments. Today, welcome, Barbara, and the floor is yours.
Thank you very much, Wolf, and welcome everybody to this seminar. Thank you for coming. And yeah, as Wolf said, I will talk about geology and the relevance of this discipline in the search for habitable environments beyond Earth. So let's get started. You should be able, okay, to see the next slide now. So I get most of the people here today will be familiar with this concept of habitability, but I want to introduce just a few concepts which is what makes a planet habitable. Well, to make a planet habitable, we need to have some ingredients which are usually associated to what is needed for life to exist, life as we know it, of course. And these are usually the presence of liquid water and a source of energy, source of carbon, and nutrients. And usually from the geological point of view, we also need a geologically active planet, meaning that life can do for a little bit without some of those elements, but not for a very long time. So if we are looking for a planet who can sustain life for a longer period, we also need some form of geological activity. So today we will talk about planet Mars, which relevance for the search for life quest is undoubtable. And well, is our neighbor. We are sharing a place in the Goldilocks zone around the sun with this planet. And the important thing of this position, so close to the sun, is that the orbit of Mars is in a range, which is called Goldilocks zone, where liquid water can be supported at the surface given a sufficient atmospheric pressure. Today, Earth had this sufficient atmospheric pressure. Today, Mars doesn't, but it probably had in the past, because as in a few slides we will see that there are geomorphological evidence that that happened in a geological past. Also, Mars, is it like an active, geological active planet? Well, yes and no. We do not see any evidence of plate tectonic, for example, as we can see on Earth, on Mars. But so it's, from this point of view, it's kind of not really active planet. But on the other side, we know that on Mars there are very large volcanic provinces that you can see highlighted in the slide, which are very important compared to the total surface of the planet. And this means that there was enough activity to put into circulation energy, nutrients, carbon, all the elements that could sustain life for a longer period. And those volcanic activity took place over a very vast and widespread period of time in the geological past of Mars. So this was somehow kind of active in the past and could have put these elements into circulation enough to sustain life for a period of time. But not least, as I said, the important part that we will focus about is the presence of liquid water on Mars. The very most astonishing element that we do see at the surface is the presence so widespread of fluvial channels all over the planet. There are two different kinds. The first ones are what are called valley networks that you can see here. There's no scale, but you can imagine that those craters are a few kilometers apart. And those are all these red lines that you can see peppered around the surface are all valley networks that carved the highlands of Mars. So they are very all over the place. So there must mean that a lot of water was present in a national geological past. Most of them are considered to be Noachian, so before 3.8 around giga years ago. And then there are outflow channels, which are different kind of fluvial channels, which are these ones on the bottom of the slide that you can see. And these are so big that you do not just see that are widely spread around, but you can definitely see them from a global map of the entire planet. Here is a slight zoom in on Kersey valleys. We are talking about tens of kilometers of wide channels, and those are thought to be younger than the valley networks. Those are expected to be Asperian in age, but as you can see, they are huge, and the flow rate that's expected for these channels when they were active is order of magnitude more than the biggest channels on Earth. So you can just imagine how much water and sediment might have been transported from the highlands toward the lowlands at a certain point during the geological past of Mars. So, of course, at this point, we know that liquid water at a certain point was definitely there. These are very, as I said, astonishing proof, but there are many different geological features that are suggesting that water was actually present in the surface, in the subsurface, on this light subsurface. And these are, for example, mud volcanoes, rootless cones, lakes, shorelines, and deltas. Today, we will focus specifically on mud volcanism and deltas. And the reason is that those two features are, in my opinion, at least, sort of end members. In fact, we do have the deltas are, of course, very important for the search for life. And they are connected to these fluvial channels that I just talked to you about. So the presence, the generation of deltas really involve huge amount of waters that was carving and flowing on the surface. But on the other hand, they are phenomena that are very confined to the surface, and for this reason are also considered to be pretty old in the geological history. On the other hand, we had mud volcanism, which is a sort of volcanism which do not involve any kind of magma, but involve the extrusion and the of water, sediment, and gases. So we still have the necessity to involve water to have mud volcanism, but since the water is stored under the surface, sometimes even kilometers of tens of kilometers underneath the surface, this water is protected from the harsh environment of the surface that it is today. So this kind of phenomenon can actually take place much younger in a geological history of Mars. So let's start from deltas. Well, I don't think I have to convince anybody of how important deltas are for the search for life on Mars. Mars 2020, if you cast a glance over the main goals of the missions, you can see how the search for life and habitability is pivotal for the researchers who conceptualize the entire mission. And Mars 2020 landed on the Jezero crater delta. So yes, this is really, deltas are really a key point for habitable environment study. And the reason is that, of course, they are very straightforward indicators for past water availability, but also they are very good environment to preserve organic matter, whether there was some in the basin where the delta was formed. So at this point, given the importance of deltas, we were wondering how many other places are there on the surface of Mars that could look like or could have the same potential that Jezero crater has. So we're asking ourselves, let's go on a global perspective and try to understand how many of those places with a very high potential of preserving life could have been present on planet Mars. And that's what we did. So you've just seen how delta look like on Mars. This is a very pretty delta. This is in general how a delta look like. So we need to have, for example, there are some key characteristics that need to be present to identify a feature on the surface as a delta. And this is how geomorphology works. Right, so we do need to have a feeding channel, and that's behind the delta. Otherwise, if the channel is missing, we might mistake an alluvial fund for delta, for example, which is very important. So to have this channel, then they are usually fan shaped with a flat top and a frontal scar. But we need to keep in mind that when we are talking about Mars, we have features that have been there, water is no longer there, and features have been dry for millions, sometimes billions of years. And so erosions take place, and also sometimes dust covering. And so we really need to be careful when we interpret features on the surface. So we went around the entire surface of the planet and tried to produce a catalog of all the deltas we could find. And we found 161 of them, which is not much for an entire planet, but is a lot, especially because 68 of them were not previously reported in any other catalog. So it was a good job. And we prepared a huge table with all the geological and geomorphological information about those deltas, and in order to study them, to try to understand where they are, what's the relationship between the delta and the place they are located in. And especially we will see in a moment that we also were very interesting in trying to understand if deltas could tell something about the possible past presence of an ocean on the northern plains, which is still debated. So let's go to it. First thing that we were looking at is, where is the delta located? So in the past catalogs that were published before, authors usually divided the basin where the delta are located into two categories, which is closed basin, which is everything that's a crater, and open basin, which is basically everything else. Usually deltas that are located at the margin of the northern plains or the outflow channels. We decided also to introduce the lake with outlets, which are basically craters, which also have an outflow. And this is because we'll see that this is connected to the morphological characteristics of deltas, which also depends on this possibility to have an outflow which is regulating the water level into the basin. Overall, just doing this kind of observation, we found out that 120 out of 161 of the deltas were located into enclosed basins. So in the first two categories that you can see here on the slide, and just 41 of them were actually located at the margin of the northern plain or in outflow channels, so a minority of those deltas, which is interesting given the amount of networks and valley networks which are flowing toward the northern plains. But as I said, it's more interesting even to notice that there are some morphologies of deltas that are actually telling something about the water level behavior at the moment of the delta formation. What's remained basically from the delta we can see today. And these are three. We have that these three different morphologies are coming from previous literature and are step delta that registered a water level rise, prograding deltas, which are the most common on Mars, which are recording water level constant, and then we do have the incised deltas, which are differently recording the water level fall. And here is what I was talking to you about, that's interesting compared to the basin where these deltas are located, because the thing is that we found that incised deltas, so deltas that recorded a falling of the water level, are present in the lake with outlets and are present in the open basin deltas, but are never present in closed basins. And on the other hand, we have the step deltas, which reported a rise of the water level, are never present in any kind of open lake. They are always present just into closed craters, which is interesting by itself because, well, we don't know, but there's this kind of a hint that in the possible ocean in the northern plains, there's no record of any water level rise, which is very interesting. But at this point, we did some few observations besides these ones. So we also were interested in understanding where those deltas are located. You see a few maps by now. You can see they are peppered all around the surface. They are mostly focused and around the dichotomy boundary. But as you can see from the first histogram here, they're really spread at very different elevations, even though there is abundance, particular abundance around the dichotomy boundary level, but this is not so strict as it was claimed before. And on the other hand, we also measured, as I was saying before, the length of the feeding channel, which is a very important feature to discriminate a delta from different morphological features. And well, we found out a very interesting thing. Here we see that the large majority of the deltas that we observed are actually fed by channels that are very short, kilometers to a few tens of kilometers long. As you can see, this is a very, very strong trend that we are having here. And this is interesting because previously in literature, it has been said that the length of the channel is a proxy for the duration of the aqueous activity. So this is sort of saying that probably most of the deltas are the result of short-lived aqueous activity, but most importantly is saying that there might be a proportional to the age of the delta itself. So having very short channels can also suggest that those deltas and the fluvial channels behind them may be much younger than previously expected. So not necessarily Noachian, for example, but they might have been Asperian or Amazonian, which is very new for what was known, it's been known up to today about the deltas and the fluvial system. So at this point we were very curious. Going to see what actually is the age of deltas is very complicated because they are very small, and using the classical technique of credit counting is very debated. So we try to approach the problem for a more original perspective. We try to see if there was a connection between the deltas and the possibility of an ocean, which also has been studied through different proxies, and try to see if there were some connections, if there was some constraints that were bonding these two events in order to sort of give a time frame of what happened on Mars. So we eliminated from our study all the deltas that were enclosed into craters, and we also took out all the deltas that were located in outflow channel, for example, because outflow channels could contain water without the necessity to actually fill the northern plate with an ocean. And we were left with 29 deltas, which is not much, but it was still enough to study. So at that point, we needed to be sure that we were talking about deltas that were actually flowing, were located at the margin of a huge basin called ocean. And to do that, we needed to be sure that the elevation lines were actually degrading from the position of the delta front toward the horizon, let's say, progressively going down as we move toward the northern plains. That's how you know that this delta is located in a basin which is not confined. In this case, it's confined to the northern plains, which is an entire hemisphere of plains, so pretty big kind of basin. And we did it. We did it on all the 29 deltas, and surprise, surprise, we found out that 23 out of the 29 deltas that we had are actually enclosed in topographic depressions. This means that there are 23 deltas out of the 29 that could be possible without filling the entire northern plain with water. It means that there are ponds where the deltas are located, and if we fill, hypothetically, those ponds with water, there's enough water to get the delta generated without any necessity of having an entire ocean. Which is very interesting, because at this point we just have 6 deltas left for the possibility to be actually connected to an ocean, which is not a large number compared to the amount of surface that we have, the dichotomy boundary that's connecting the highlands to the lowlands. Nonetheless, we went there and examined the morphology and the ages and everything that we could have known about those deltas and observe. And I will describe one specific delta to you, which is very, very interesting in my opinion, which is the Memonia delta. This delta, which is the A delta here on the left, is very unique. And the reason is that we were able, with this delta, to really constrain the moment in time where the delta was actually active. In fact, we usually do have the time, the age of the unit that the channel is carving, which needs to be older, of course, of the channel itself, but that's usually it. But if you pay attention here, you can see that we do have a flow, another unit, which is covering part of the delta, meaning that at that point in time, when the unit that's covering the delta was deposited, the delta was no longer active, because we do not see any kind of overflow over this unit. And this is extremely important, because at this point, if we date also the unit that's covering the delta, we can also have a moment that's kind of putting a constraint to the final moment where the delta could have been active. And that's exactly what we did. We dated the 2 units and found out that this is very well constrained. We found that this delta needed to be active in between 3.6 and 3.3 gigayears ago. So we are in the Asperian age. We were able to constrain very, very tightly. And as I said, we are not in the Noachian age where most of the activity, the fluvial activity, is supposed to be, but we were in the Hesperian much later. And thanks also to additional studies, we were also able to constrain it even more, possibly to a moment enclosed in between 3.4 and 3.3 gigayears ago. So what's it saying is that possibly we have that an ocean might have been present in that moment in time on the surface of Mars, because there is no evidence that these deltas were otherwise confined into any other type of topographic depressions. So this is the power of the application of geomorphology to the surface of a planet to really understand what happened there. It is to be said that we are talking about one delta, which is not much, and it's a little bit too little to really describe everything that's happened on an entire planet. In fact, we were hoping to see a trend on the 6 deltas that were actually located at the margin of the lowlands, seeing that the ones that were at a higher elevation were also older, and expected to be the ones that are located at lower elevation to be younger, because of a retreating ocean would act like that. But as you can see from this graph here that we provided, this trend is not visible. This might be because there are too little points, too little information. This might be a reason, we don't really know, but the trend is not there. So it's very hard to really reconstruct the entire history. But this Memonia delta is really giving a hint about what might have happened pretty recent, like midterm recent geological past of Mars. So this is what we did with geomorphology, talking about deltas on the surface of Mars. And yes, we still thought that the event might have been older. We found out this might have been younger, but still is not super recent. Now we move on to the second end member, the ones that is really digging down the surface and really coming more recent in time. Let's talk about these mud volcanoes. This is a study that we finished last year, and that's what I want to talk to you about, because this is a very interesting area on the Martian surface. It's located here in the northern lowlands, and we are talking about features which are located on early Amazonian, late Hesperian sediments. So we are already sure to be much younger in time. And well, we do have an entire field of those mud volcanoes. We're talking about more than 9,000 of small volcanoes around 0.5 kilometer in diameter. All together, here you can start to see a hint of how they look like. I will show you more in detail in a few moments. And as you can see clearly, these are not just randomly distributed on the surface, but these features are clearly coalescent, sometimes just lines, sometimes coalescing along very clear lines that you can see all, like you can have an overview of here on this image. So the situation was very interesting. And so at this point, we were very interested to understand what happened. And so, most of all, we were interested in understanding where all those materials, all those sediments and water and possibly gases that generated the mud volcanoes were coming from. So this is how mud volcanoes usually work on Earth, where we have a lot of information, differently from Mars. So we usually have one or more source rocks, source layers that provide sediments and fluids. And then when these fluids and sediments that are buoyant and get to reach the surface, we actually generate the mud volcano that we can see from orbital images. Here are some beautiful images from Azerbaijan. Here are some photos that I was able to take in Iceland, thanks to Wolf Summer School. And this is how mud volcanoes look like on Mars. This is a previous work, so I will try to stay as little as possible on geomorphology and try to focus on the structural part. But this is how they look like. So we went a little bit into detail in which are the characteristics, the key elements that really describe them as mud volcanoes, and not different kind of morphologies that can actually look like as little mounds on the surface of a planet. And we also put together this information, this morphological information at the time, with also nighttime infrared information, which was also not only constraining those features as vents, but was also telling us that those specific vents were very likely formed by unconsolidated fine-grained materials, which is very consistent with mud volcanism instead of conventional magma volcanism. And so we were very, very sure that from the geomorphological point of view, we were talking about mud volcanoes. So at this point, in the past year, we were differently interested in understanding where the material was coming from. At this point, we knew we were talking about mud volcanoes, but we didn't know where the source layers were. So we switched from the real case scenario that we have on Earth to try to understand, to model what's happening on Mars. And the technique that's used is called fracture analysis, which is a statistical procedure based on the spatial distribution of the vents, and basically allows us to estimate the extent of the connected fractures that allow the movement of materials from somewhere in the subsurface to the surface. Because if you think about it, you need a conduit that actually connects the subsurface source to the surface where you do see the feature. And that's what this analysis is looking at. And also we try to implement one more analysis, which is more superficial, because fracture analysis can actually tell us where the source is independently of where it is. It can be a few kilometers, can be tens of kilometers. Fracture analysis will tell us. It will tell us if there's one source, two sources, three sources, and so on and so forth. And then we implemented also fracture spacing analysis, which is a little bit shallower kind of analysis, but it is still a proxy since we still have these alignments in our area, which are very likely to be fractures along which the mud volcanoes developed, using these fractures as conduits for material resurgences. And this is again, fracture spacing, in fact, is a proxy for the thickness of the brittle layer that's fractured, so the layer that we are actually observing from orbital images. And here are the results. So this is the table that sum up all that we found. As you can see, we do not have 9,000 points. The reason is that we are talking always about spatial distribution. So we cluster together the points, the alignments of volcanoes, and measured spatial distribution. So we clustered them and work on groups of vents and groups of alignments in order to have statistical significance on our analysis. All the points that are depicted with a dot in our table are the results of fractal analysis, while the results that are represented with a star are the results of fracture spacing analysis. And let's start. You can clearly see that these are clustered into three clear levels. This is depth, and these are the clusters basically that we used. And you can clearly see that we have highlighted three different depth levels. First one is incredible because you can see that the results that we obtain from fracture analysis and the fracture spacing analysis, which are relying on two different kind of data sets, so they are not contaminated one another, are giving back very, very similar results. They are clearly pointing out that there is a level, a first mechanical discontinuity around 4 to 5 kilometers down the surface. And this is very compatible with the fact that we are in the northern plains, where we possibly will have this amount of kilometers of brecciated materials or reworked materials, poorly consolidated materials that are infilling basically the lowlands due to all the sediments that were carried from the highlands toward the lowlands during the most ancient geological history of Mars. So this is astonishingly good result. Then we moved down and we can see that we have another pack of results which are very confined around the 20 kilometers. And at this point we were asking ourselves what this can be, because the first one was very compatible with the location, but what could be there at 20 kilometers depth, around kilometer more, kilometer less? And we looked for some information, previous studies that have been done in literature, and we found out that previous models located at around this depth, at this same location where the field is found, which is pretty big, but is pretty well constrained in at one latitude. There's it's hypothesized, according to models, the presence of the transition from a cryosphere to the dry bedrock or hydrosphere, depending on the availability of water. We still don't know. And so this is incredibly interesting because this is a very good place to look for a source layer, because any event that could usually trigger mud volcanism on Earth, which are many, could generate different, usually are events that alter the temperature or pressure or of some layers in the subsurface, and this start the buoyance of materials. And well, if I had to guess, I would guess that the base of the cryosphere is the most prone to, the most sensitive to TP variations. And so this is very good that we are finding this specific layer as a source layer to fracture analysis. Moreover, we also have to say that this specific boundary, let's say, that has been modeled in the past is not just the cryosphere base, but is the clathrate-rich cryosphere base, meaning that possibly these ices that are stored or have been stored during the mud volcanoes formation in the subsurface might have been in a form of clathrates, which are ices which can bear also a huge amount of gases. And these, in the moment that these, for any reason, are melt, could release a larger amount of volatiles that could increase the buoyance pressure and help those materials to really go up to the surface. So this is incredibly interesting, I think, for the perspective of the habitability that we are trying to have in this work. Then there is the final source layer here, which is possibly a little bit less interesting, but still, I would like to give you an idea of what it is. And this possibly is the bridge-adductite transition. In fact, it has been modeled plenty of time, and in a sort of recent Amazonian geological past, it's hypothesized to be around 50-55 kilometers, and that's exactly what we see. And that's very good also because we never see anything that's deeper than that, and that would be consistent with the fact that if at that point we do start having a ductile behavior of rocks, we have no fractures anymore, and so it's very consistent with the fact that that's the maximum reach the fracture can have in the crust. Last thing I would like to point out is that not only those results were very good by themselves, and they were going very good with different past literature about what they're supposed to found at those specific depths, but also we're pretty close to what's inside. So in fact, here there are one image, but there have been few publications that are trying to reconstruct the stratigraphy of the crust, which is still highly debated, still under discussion. But the guesses that have been done are not that far away from what we are observing. We need to remember, first thing, that Insight is not located nearby the study area that we are studying here. There are a few, well, more than a few sometimes of latitudinal degrees northern, while Insight is much closer to the equatorial region. But then, so we can expect to have some variation. But then we still see that there's not so different kind of hypothesis. They hypothesize that at the Insight landing site, lowlands, they might have one layer 9 kilometers, then 124, then might have 40 kilometers, even a little bit deeper around the planet, the Moho. And so this is not that far away from what we saw with fracture analysis and fracture spacing analysis. So summing up everything, this is what we were able to do with structural geology, because this is what all these studies basically is founded, is based on the principle that rocks were fractured according to specific criteria that are usually intrinsic of the rock itself, and that's been tested plenty of time on planet Earth. And so thanks to these studies that are based on how rock fractures and break, we were able to reconstruct the mechanical layering underneath this large field of mud volcanoes on Mars, and really we were able to see where the materials that have been extruded were coming from. And it is also pointing toward the direction that we might have had, well, ices, possibly water in the subsurface in pretty recent time, because also in a previous work, we were able to date those mud volcanoes. And the hypothesis is that these are around 300 to 400 million years old. And even if we are underestimating the age of those features, we're still pretty sure we are in the Amazonian period, so pretty recent times for having water. So these are also, I would like to say, that are a good candidate, in my opinion, for future research, for future missions. If we try to understand how organic matter might be preserved in this situation, this is a very interesting area, because those mud volcanoes are actually sampling the very deep subsurface and bringing those materials to the surface where we can actually look at them. So on this note, I'd like to thank you. At this point, I presented all I wanted to say about our T1 members, the deltas and the mud volcanoes, and how geology, and specifically geomorphology and structural geology, are really helping to understand where to find habitable environments on planets. I focused on Mars, but similar studies can be provided on different planets. And thank you so much for your attention. We're very open to questions.
So just a moment. Yes, Jan Henrik, please.
Yes, hi. Thank you for your very interesting talk. So I'm not by any stretch of the imagination a geologist. So maybe this is a stupid question. So I can understand why you would lose the evidence of some of the deltas due to erosion impacts, other factors, but there shouldn't be any false positive in the sense that you mistake some geological formation for a delta, which it isn't. Is that right?
My guess is, if I understand your question, is can we mistake different things for deltas? Is it that what you're asking?
Yeah. I mean, so yeah. False negatives, yeah. So you might miss a delta because it is morphed in some way, but you shouldn't get false positives from your analysis. Is that right?
Well, we very hope that that's true. And actually, the biggest problem, and there have been some publication about it, is to confuse deltas with alluvial fans, which look pretty similar because those are, yeah, they're fan-shaped and they're sort of conical, but they are missing the frontal scarp. They usually do not have the channel that's feeding them. And the main difference from the environmental point of view is that alluvial fans do not really need to have a basin filled with water to be generated, and the delta does need a basin that's filled with water, and this is also very important considering the perspective of the habitability. And that's the main feature that might get lost in translation. And well, we try to be very careful about it. There have been some publication about it that are trying to really constrain the key elements to really distinguish these features from Wilson and et al. And co-authors, if I'm not wrong. But yeah, well, theoretically in our catalog, they shouldn't not be present, hopefully. But yes, this is how false positive could appear. Like, this is the main kind of features that I would say could be mistaken for a delta in the observations. So something that's still related possibly to the flow of water on the surface, but not really correlated to the presence of channel, let's say long-lived channel, or anyway, something that was long-lived enough to carve the units where it was standing on, and then a basin that's filled with water where the delta needs to be there. And yeah, sometimes it's difficult because you have erosion, and that's sometimes you do not have any 3D information because these are not very huge features. And so if you just have the MOLA, which is the global 3D DTM of Mars, sometimes those are too small to actually be able to have some cross sections, for example, and so you could miss the frontal scarp, and this could get you mistaken in the interpretation. That's what I would say, but I wouldn't say that, I mean, too many people observe the catalog to get some false positive in there, I hope.
Okay, so thank you.
Oh, welcome.
Another question by Flores van der Pak. What are the size of the deltas? Could you find the sources of some of the rivers?
So this is a very good question. The sizes is very variable, but they are still pretty small. We are always talking about few kilometers. And so this is making very hard, as I was saying, dating these features, because usually to have a meaningful crater counting, you need minimum areas to work on, and so that's still debated. And concerning the sources of the rivers, that's what we are working on right now. So it's a little bit of an ongoing answer that I can give you, and that's very hard to tell. There is no clear source because there's no clear idea of, for example, where ices were and when ices were present. There's a lot of modeling about it, and there's a lot of discussion going on about it. Some people say that the ices were covering part of the highlands just in the late Noachian period, but this would not explain much younger activity that we are seeing. We do not know anything about any possible weather kind of circle, so we do not know if there was some snowing going on or rain, and that also could contribute, of course, to giving to providing a source for the water in rivers. And there's also big question mark on groundwater circulation on a global scale. So this is a very good question with very few answers to it. There are a lot of other questions connected to this question, but few answers, I'd say.
There is another question by Daniel Lecour. He asks, where you mentioned earlier that you found the deltas on Mars to be shorter than expected. Do you think this could have been due to covering up from other geological processes rather than due to them being younger?
So the question is if the channel were actually longer and we just have the tip of the channel visible today. If this is the question, I think this is not the case, because we do have preserved very long channels. So if this was the case, I would expect it to have many deltas also connected to very long channels, valley networks, and some of them also connected to shorter channels. And at this point, I could wonder whether look at them and really try to understand. Well, first of all, I have to say also that there is no evidence of covering of any kind of erosional or obliteration that came after, but they were pretty pristine sort of channels, and that's by itself I think is an answer. But yet again, also I think that the distribution is saying something. It's more likely, in my opinion, and this is just my opinion, is that deltas that were present on longer valley network at the tip of longer valley network might have been sort of eroded, or they were present at the boundary of the lowlands might have been destroyed due to the water level fluctuation, I'd say. I don't know, this is just a guess, this is an educated guess, but in this where we are trying to follow up, we are also wondering why maybe deltas are very easy to destroy compared to the channel itself, and so whether the delta is very recent, then it's higher possibility to get preserved, so we saw much more of them with the respect of older counterparts. I'd say possibly this might be an answer, but I would exclude that the reason why there is this correlation is because channels have been covered up or eroded.
Okay. Josep, please.
Sure. Well, first of all, thanks, Barbara, for so exciting talk. Really interesting. Can you hear me well?
Yeah.
Oh, excellent.
Thanks.
Okay. Well, I'm specialized in meteorites, particularly on Martian meteorites. And you know, from the different classes of meteorites we have from Mars, it's quite obvious that we have some quite relevant evidence of aqueous alteration in the surface of Mars. But of course, Martian meteorites are quite biased towards higher strength materials. That is just probably the opposite to these terrains you have been describing, no, in your talk. So first of all, just saying an assessment, no, that really, if we want to understand possible, you know, signatures of life in Mars, we need to do sample return missions or even in situ analysis of all these regions. And the question is, if you have the chance to choose exactly which is the place where you should send a sample return mission, what you will choose? I mean, a delta, a mad volcano, or another place? Thank you.
Thank you. This is a very tricky question. Well, yeah, you're absolutely right. There's a lot to take into account also from the geochemical point of view, which is beyond my the interest of this talk. And but this is very important. I know that catalog has been compiled about it, and this is also of our interest. We are trying to compile an entire catalog of all geological features that are water related on Mars right now at the DLR. And so, yeah, that's very important to really understand areas like, for example, have a higher concentration of water related features, even from the geomorphological point of view and from the geochemical point of view, for example. If I have to guess, well, we already have one sample return missions on Delta, so let's say that that's covered, and I would go with the map volcanoes. I think that this might be a problem for planetary protection because they're pretty north, and I'm not super expert about the thing, but I'm pretty sure that we are a little bit too north to be safe about planetary protection, but I don't know. And I would go with that. I would definitely be curious to understand what those mud volcanoes are actually sampling from so deep down the subsurface, right? Because of course these were very recent in a geological perspective, but they probably did not happen yesterday. So everything that's on the very surface of those mud volcanoes probably has been obliterated. So I'm not an expert on long-lived biosignatures, but I guess that being exposed to the harsh environment of the surface would have probably obliterated traces of organic matter or preservation at the very surface. But these are small features if we compare to others, but they're still a kilometer of volcanoes, right? So we can still court them and try to see what's at the base, like the first layers that have been erupted, and then maybe there's a possibility that if there's something that was living back at the source layer, or even just the chemical composition possibly might have been preserved down those layers, and that's what I would go look for. That's my guess.
Thank you, Barbara. Then let's go to Matt.
Let's go to Mars. Yeah, hopefully.
Thank you.
Thank you.